For more than 50 years, no human being crossed the invisible boundary of deep space beyond low Earth orbit. Think about that for a second. Entire generations were born, grew up, and built the digital age, while the farthest footsteps of humanity stayed frozen in old film reels from Apollo. Those images are still extraordinary, but they are not just nostalgia. They are proof that our species once did something impossibly hard, and then, for a long stretch of history, chose not to repeat it. When Apollo ended, the moon did not disappear. It hovered in the night sky as a permanent question mark. Every month it passed through phases like clockwork, silently reminding us that a world only about 3 days away by spacecraft had become, politically and economically, farther than ever. In those decades, we learned to live in orbit, built stations, launched probes to every corner of the solar system, landed robots on Mars, and still did not send another crew around the moon. The distance was never the only obstacle. The real barrier was systems-level commitment. Now that barrier is shifting. Artemis is not a retro replay of Apollo with better cameras. It is a redesign of the entire logic of lunar exploration. Apollo proved we could reach the moon. Artemis is trying to prove we can operate there repeatedly, safely, and with enough cadence that missions stop being isolated miracles and start becoming infrastructure. That difference changes everything. Even the name carries that intent. In Greek myth, Artemis is the twin sister of Apollo, and in this context, the symbolism is deliberate. This is a sibling era, not a copy. One program proved defeat. The next program must prove the continuity. Artemis II, the first crewed lunar mission of this new architecture, is not just another launch date on a calendar. It is a stress test of whether half a century of aerospace evolution can converge into reliable deep space operations with humans on board. Why go back to the moon at all, when Mars captures headlines and deep space telescopes reveal galaxies at cosmic dawn? Because the moon is where ambition meets accountability. Mars is the horizon. The moon is the workshop where we learn to build the tools, protocols, and survival habits required to reach that horizon without gambling, lives, and optimism alone. If Earth orbit is training ground, the moon is the first real field deployment. There are hard facts behind that argument. The moon is close enough for comparatively short transit times, but far enough that crews cannot be rescued quickly. Communications have delay. Power strategy matters. Thermal design matters. Dust control matters. Medical autonomy matters. In other words, all the uncomfortable problems of deep space begin to appear at lunar distance, but in a domain where iterative missions are still feasible. It is the most practical place to learn hard lessons before the stakes scale up even further. The moon is also a scientific archive, unlike anything on Earth. Our planet is geologically active and constantly rewriting its own surface through erosion, weather, plate tectonics, and biology. The moon preserves scars from ancient impacts that were erased here long ago. Studying lunar geology helps reconstruct the violent early history of the inner solar system and sharpens our models of how Earth became habitable. So when we send humans and instruments there, we are not just opening a transportation corridor, we are opening a time capsule. And then there is the resources question, which is not science fiction anymore. Polar regions contain evidence for water ice in permanently shadowed areas. Water in space is never just water. It is life support, radiation shielding, and, through electrolysis, a path to rocket propellants. If extraction and processing technologies mature, the moon could become not simply a destination, but a logistics node that supports deeper exploration. That possibility is one reason engineers, agencies, and companies around the world are moving fast. What makes this era different is not one rocket or one capsule. It is architecture. Government systems, commercial landers, international hardware contributions, robotic precursor missions, and planned orbital infrastructure are being designed to interconnect. Artemis already validated key elements of this chain with an uncrewed mission profile, the sent Orion around the moon and back. Artemis II is meant to validate the human layer of that architecture under real mission conditions. So this is not about flags and footprints alone. It is about turning rare triumph into repeatable capability. Apollo was a sprint of extraordinary intensity. Artemis is trying to build the marathon framework, where each mission leaves behind not only memories, but also operational maturity, better procedures, better hardware reliability, better risk models, better integration between public and private systems, better confidence that the next flight can be safer than the last. That confidence will not come cheaply. Deep space missions are brutally unforgiving to weak assumptions. You must keep crews alive in radiation environments, manage finite consumables, navigate with extreme precision, land through dust and rough terrain, and maintain systems that cannot call roadside. Assistance. Every subsystem is coupled to every other subsystem. A thermal issue can become a power issue. A power issue can become a life support issue. In spaceflight, complexity does not stay in its lane. This is why the central question of modern lunar exploration is not, can we get there once? The central question is, can we build a system that can do it again and again while learning, adapting, and reducing risk over time? That is the threshold between heroic exploration and sustainable presence. Cross that threshold, and the moon becomes part of civilization's operational map, rather than a rare destination reached only by exceptional historical moments. And there is a human dimension that numbers cannot fully capture. Every lunar mission reframes Earth. Astronauts describe looking back at our planet not as a set of countries, but as one connected biosphere wrapped in a thin atmosphere. That perspective is not poetic decoration. It can influence how we think about climate, conflict, cooperation, and long-term stewardship. The moon, paradoxically, can teach us how to take better care of Earth. So we stand at a hinge point. Behind us is the era when lunar travel was a heroic memory. Ahead is the possibility that lunar travel becomes a practice discipline. Whether that happens depends on engineering quality, policy choices, international trust, and relentless operational honesty. If we get those pieces right, the moon stops being a monument to what we once achieved and becomes the proving ground for what we can repeatedly achieve together. From here, the story becomes technical in the best possible way. We're about to follow the mechanics of the journey itself, from launch energy to transfer trajectories, from orbital insertion to descent and landing, from elegant equations to harsh constraints. This is where dream meets physics, and physics always tells the truth. Let's begin. To journey to the moon is to embark on a voyage that spans 250,000 miles, crossing the vast gulf of space that separates our world from its closest celestial neighbor. But how do we make this journey? What are the mechanics that transform the dream of lunar travel into reality? It begins with understanding the forces that govern our universe. Gravity, momentum, and energy are the invisible threads that weave the tapestry of spaceflight. Imagine the Earth and the Moon as two dancers in a cosmic waltz, their movements dictated by the pull of gravity. To travel from one to the other, we must choreograph our spacecraft's path with precision, using the laws of physics to our advantage. The first step is launch. A spacecraft must escape the grip of Earth's gravity, a feat that requires immense energy. This is where rockets like NASA's Space Launch System, or SLS, come into play. The SLS is a behemoth, the most powerful rocket ever built, designed to propel the Orion spacecraft beyond low Earth orbit and set it on a course to the moon. But launch is just the beginning. Once in space, the spacecraft must perform a maneuver known as a translunar injection, or TLI. Think of it as a push that sets the spacecraft on a trajectory toward the moon. This maneuver is carefully calculated to ensure that the spacecraft reaches the moon's vicinity at the right time and place. It's a bit like aiming a dart at a moving target, with the added complexity of accounting for the gravitational pull of both the Earth and the moon. One of the most elegant solutions to this challenge is the free return trajectory. This path takes advantage of the moon's gravity to loop the spacecraft back toward Earth without the need for additional propulsion. It's a safety net, a way to ensure that the crew can return home even if something goes wrong. The Apollo missions famously used free return trajectories, and they remain a key consideration in modern mission planning. But not all missions follow this path. Some require more precise maneuvers to enter lunar orbit. This is where the concept of delta V comes into play. Delta V, or change in velocity, is a measure of the energy needed to change a spacecraft's speed and direction. Think of it as the currency of space travel, with fuel as the budget. Every maneuver, from entering lunar orbit to landing on the surface, requires careful management of this precious resource. Modern spacecraft like SpaceX Starship Human Landing System, or HLS, are designed with these challenges in mind. The Starship HLS is a marvel of engineering, a fully reusable spacecraft capable of carrying astronauts and cargo to the lunar surface. Its design includes in-orbit refueling, a technique that allows it to carry out multiple missions without returning to Earth. This approach is a stark contrast to the Apollo-era lunar module, which was a one-time use vehicle. Commercial landers developed under NASA's Commercial Lunar Payload Services, or CUPS, program add another layer of innovation. These smaller, robotic craft are paving the way for human missions by delivering scientific instruments and technology demonstrations to the Moon. Each mission contributes to our understanding of the lunar environment and our ability to operate on its surface. As the spacecraft approaches the Moon, it must perform a lunar orbit insertion maneuver. This involves firing its engines to slow down and allow the Moon's gravity to capture it. From there, the mission enters its final phases, preparing for descent and landing. These steps require precision and coordination as the spacecraft transitions from orbit to the lunar surface. The journey to the Moon is a testament to human ingenuity and the power of collaboration. It is a dance of physics and engineering, a delicate balance of risk and reward, and it is a reminder that every step forward is built on the achievements of those who came before. The Apollo program laid the foundation, but the Artemis program is building the future. As we look ahead, the mechanics of lunar travel will continue to evolve. New technologies, new spacecraft, and new partnerships are reshaping what is possible. But the principles remain the same, harnessing the forces of nature to chart a course through the cosmos. And as we stand on the threshold of this new era, we are reminded that the journey to the Moon is not just a technical challenge. It is a human endeavor driven by curiosity, ambition, and the unyielding desire to explore. In the next chapter, we will delve deeper into the challenges of lunar exploration. What does it take to land safely on the Moon's surface? How do we navigate the trade-offs between fuel efficiency, safety, and mission success? And what role does technology play in overcoming these obstacles? The answers lie in the intricate dance of science and engineering that makes lunar exploration possible. The Moon is a world of extremes. To reach it, we must first overcome the invisible forces that bind us to Earth. Gravity, the great sculptor of the cosmos, is both our adversary and our ally. To escape its grip, we need energy, lots of it. This energy is measured in delta V, a term that describes the change in velocity required to move from one place to another in space. Think of delta V as the currency of space travel. Every maneuver, every orbit, every landing has a price, and that price is paid in fuel. Imagine, for a moment, that you are planning a journey to the Moon. You start on Earth, where gravity holds you firmly in place. To break free, your spacecraft must accelerate to a speed of about 11 kilometers per second, Earth's escape velocity. But in practice, the journey is broken into stages, each with its own delta V requirement. First, you need about 3.2 kilometers per second to reach low Earth orbit. This is the first leg of the journey, where the rocket equation begins to show its teeth. The more mass you want to carry, whether it's scientific instruments, life support systems, or astronauts, the more fuel you need. And the more fuel you carry, the heavier your spacecraft becomes, requiring even more fuel to lift it. This exponential relationship is the essence of the rocket equation, a mathematical truth that governs every space mission. Once in low Earth orbit, the next step is to perform a translunar injection, or TLI. This maneuver requires another 3.2 kilometers per second of delta V. Imagine aiming a dart at a moving target, but the dart is your spacecraft, and the target is the Moon, hurtling through space at nearly 3,700 kilometers per hour. The timing must be perfect. Too little velocity, and you'll fall back to Earth. Too much, and you'll overshoot the Moon entirely. The precision required is staggering, and every gram of fuel must be accounted for. Now, let's put this into perspective with a worked example. Suppose your spacecraft has a dry mass of 10,000 kilograms and carries 40,000 kilograms of fuel. Using the rocket equation, we can calculate the delta V it can achieve. The equation is simple in form, but profound in its implications. Delta V equals the exhaust velocity of the rocket engine multiplied by the natural logarithm of the initial mass divided by the final mass. If the exhaust velocity is 4,500 meters per second, a typical value for a chemical rocket, then the delta V is approximately 9 kilometers per second. This is just enough to reach the moon and return, assuming perfect efficiency. But real missions are never perfect. Margins are added, contingencies planned for, and every decision becomes a trade-off between mass, fuel, and mission objectives. The delta V is only part of the story. The moon is not just a destination, it is a harsh and unforgiving environment. One of the greatest challenges is radiation. Beyond the protective cocoon of Earth's magnetic field, astronauts are exposed to galactic cosmic rays and solar energetic particles. These invisible bullets can damage cells, increase cancer risk, and impair cognitive function. During the Apollo missions, astronauts spent only a few days in space, limiting their exposure. But future missions, like those planned under Artemis, will involve longer stays and greater risks. Shielding is the first line of defense. Materials rich in hydrogen, like polyethylene, are effective at blocking radiation, but they add mass, a precious commodity in space. High-Z materials like lead offer protection against certain types of radiation, but are less effective against others. Engineers must balance these trade-offs, designing habitats with storm shelters for solar events and exploring the use of lunar regolith as a natural shield. Timing missions to avoid solar maximums and monitoring space weather are additional layers of protection. Imagine standing inside a lunar habitat during a solar storm. The warning comes from Earth, a coronal mass ejection is on its way, and you have hours to prepare. You move to the storm shelter, a small, heavily shielded room within the habitat. Outside, the radiation levels spike, but inside, the shielding holds. This scenario is not just a thought experiment, it is a reality that future astronauts will face. The design of these habitats is a testament to human ingenuity, balancing the need for protection with the constraints of mass and cost. Then there is the challenge of landing. The moon's surface is a patchwork of craters, boulders, and dust. Precision is paramount. Modern landers use a combination of throttleable engines, hazard detection systems, and autonomous navigation to ensure a safe touchdown. LiDAR and vision-based systems map the terrain in real time, while algorithms calculate the best landing site. But even with these advancements, the interaction between rocket plumes and lunar regolith remains a concern. The fine abrasive dust can damage equipment and obscure visibility, complicating the final descent. Imagine piloting a lander during the final moments of descent. The engines roar, kicking up a cloud of dust that envelops the spacecraft. The instruments guide you, but the visibility is near zero. You rely on the lander's autonomous systems to find a safe spot, trusting the algorithms and sensors to do their job. When the lander finally touches down, the dust settles, revealing the stark beauty of the lunar surface. This is the culmination of years of planning, testing, and innovation. Commercial partners like SpaceX with its Starship human landing system are pushing the boundaries of what is possible. Starship's all-propulsive descent and refueling capabilities promise greater payloads and more flexible mission profiles. However, these innovations come with their own set of challenges, from the logistics of in-orbit refueling to the increased delta V requirements for returning to Earth. As we refine these technologies, we are not just solving problems, we are laying the foundation for a sustainable presence on the moon. Each solution, each breakthrough, brings us closer to a future where lunar exploration is routine. And as we look ahead, we must remember that the moon is not an end in itself. It is a stepping stone, a proving ground for the technologies and strategies that will one day take us to Mars and beyond. The Artemis program is a symphony of ambition and engineering, a modern-day odyssey to the moon. At its heart lies a complex architecture designed to make lunar exploration not just possible, but sustainable. To understand this, we must first unravel the intricate web of spacecraft, missions, and partnerships that form the backbone of this endeavor. Let's begin with the Artemis program itself. At its core is the Orion spacecraft, a capsule designed to carry astronauts safely to lunar orbit and back. Orion is launched atop the Space Launch System, or SLS, the most powerful rocket ever built. Together, they form the foundation of NASA's lunar ambitions, but Artemis is not a solo act. It is a collaborative effort, drawing on the expertise of international partners and commercial companies to create a robust and flexible system. One of the key innovations of Artemis is the Lunar Gateway, a small space station that would orbit the Moon. Think of it as a staging post, a place where astronauts can transfer between Orion and a spacecraft that will take them to the lunar surface. This is where SpaceX Starship Human Landing System, or HLS, comes into play. The Starship HLS is a fully reusable spacecraft designed to ferry astronauts and cargo between the Gateway and the Moon. It is a marvel of engineering, capable of in-orbit refueling in multiple missions without returning to Earth. But Artemis is not just about crewed missions. The Commercial Lunar Payload Services, or COPS program, is sending robotic landers to the Moon to deliver scientific instruments and technology demonstrations. These missions are paving the way for human exploration, testing the technologies and gathering the data needed to support sustained operations on the lunar surface. Now, let's dive deeper into the logistics that make this all possible. Imagine the intricate ballet of tanker flights required to refuel a spacecraft like SpaceX Starship in orbit. Each tanker must launch, rendezvous, and dock with precision, transferring its payload of fuel before returning to Earth. This process is not just a technical challenge, it's a logistical masterpiece. Picture a fleet of tankers, each one meticulously scheduled, their launches timed to the second to ensure the Starship is ready for its journey to the Moon. This cadence of flights is akin to a supply chain in the sky, where every link must hold firm to support the mission. Once on the lunar surface, the challenges multiply. Astronauts will need habitats that can withstand harsh environments, rovers to explore the terrain, and a steady supply of essentials like food, water, and oxygen. This is where the concept of a lunar depot comes into play. Imagine a central hub on the Moon, stocked with supplies and equipment ready to support missions as they arrive. This depot will be resupplied by robotic landers, each one carrying a carefully chosen payload to meet the needs of the astronauts. It's a bit like running a remote outpost in Antarctica, where every shipment is a lifeline. International partners are key players in this endeavour. The European Space Agency's service module for Orion is a critical component, providing power and propulsion for the spacecraft. Canada's contribution of a robotic arm for the Gateway will enable complex operations in lunar orbit. These partnerships are not just about sharing the workload, they are about building a global community of exploration. Each partner brings unique expertise and resources, creating a program that is greater than the sum of its parts. Commercial companies, too, are reshaping a landscape of lunar exploration. Programs like CLEPS are leveraging the agility and innovation of private industry to deliver payloads to the Moon. Companies like Astrobotic and Intuitive Machines are developing landers that can carry scientific instruments, technology demonstrations, and even commercial cargo. This approach not only accelerates the pace of exploration, but also opens the door to new opportunities, from resource extraction to tourism. Recent developments have underscored both the progress and the challenges of Artemis. The decision to move the first crewed surface landing to Artemis IV reflects the complexity of integrating new technologies and partnerships. At the same time, milestones like the upcoming Artemis II flyby and the Gateway's evolving schedule demonstrate the program's momentum. On the commercial side, docking and refueling tests for the Starship HLS are paving the way for its role in lunar missions, while CLEPS deliveries are providing critical data and experience. As we look to the future, the Moon becomes more than just a destination, it becomes a stepping stone. It is a place where we can test the technologies and strategies that will one day take us to Mars and beyond. But it is also a mirror, reflecting our aspirations and our ingenuity. The Artemis program is not just about reaching the Moon, it is about learning how to stay, how to thrive, and how to build a future among the stars. And so, as we prepare for the next chapter of lunar exploration, we must ask ourselves, what does it mean to make the Moon a part of our everyday lives? How do we balance the ambitions of nations and the opportunities of commerce? And what role will humanity play in shaping this new frontier? These are the questions that will define the next era of space exploration as we move from the technical challenges of lunar missions to the human experience of living and working on another world. Imagine standing on the Moon, gazing back at Earth, a fragile blue marble suspended in the vastness of space. For the astronauts who have made the journey, this view is more than a sight, it's a profound shift in perspective. But what does it mean to live and work on the Moon? not just for a few days, but for weeks, months, or even longer. This is the question we must grapple with as lunar exploration moves from fleeting visits to sustained presence. The human experience of lunar missions is unlike anything else. The silence of the lunar surface, broken only by the hum of life support systems, contrasts sharply with the bustling activity inside the spacecraft. Astronauts must adapt to the isolation, the delay in communications with Earth, and the relentless precision required to survive. Shore missions, like those of Apollo, are sprints intense, focused, and fleeting. But longer stays demand a marathon mindset, a balance of work, rest, and the psychological resilience to endure. Life on the Moon is a study in contrasts. The barren beauty of the landscape, with its sharp shadows and brilliant sunlight, is both inspiring and alien. Daily routines, maintaining equipment, conducting experiments, and simply staying healthy become acts of survival. Every breath, every sip of water, every calorie consumed is a triumph of engineering and planning. And yet these routines also connect us to the explorers of the past who faced their own frontiers with courage and ingenuity. But lunar exploration is not just a human story, it's an economic and ethical one as well. Who pays for these missions and who benefits? The Moon offers immense opportunities, scientific discoveries, commercial ventures, and even tourism. Mining lunar resources could fuel not only moon bases, but also deeper space exploration. Yet this raises profound questions. How do we ensure that the Moon's resources are used responsibly? Who has the right to extract them, and under what rules? The Artemis Accords and other international agreements are a start, but they are just the beginning of a much larger conversation. Governance and policy will shape the future of the Moon as much as technology. The Artemis Accords emphasize peaceful exploration and international cooperation, but not all nations are signed on. Questions of property rights, environmental stewardship, and equitable access remain unresolved. The Moon is a shared heritage of humanity, but how do we balance that ideal with the realities of competition and national interests? Safety, equity, and access are central to this discussion. Who gets to go to the Moon, and why? The selection of crews, the balance between public and private missions, and the distribution of risks and rewards will determine whether lunar exploration benefits all of humanity or just a privileged few. As we look to the future, we must ask, how do we make the Moon a place for everyone, not just the wealthy or the powerful? And what might that future look like? Imagine a Moon where flights are as routine as trips to an airport hub, where scientists, engineers, and even tourists come and go. Picture a network of lunar outposts, connected by commerce and collaboration, each one a stepping stone to the stars. This vision is not science fiction. It is the logical next step in our journey as a spacefaring species, but it will take time, effort, and a commitment to shared values to make it a reality. As we stand on the cusp of this new era, the Moon challenges us to think beyond the immediate and the practical. It asks us to consider what kind of future we want to build, not just on its surface, but for humanity as a whole. The Moon is more than a destination, it is a mirror reflecting our hopes, our fears, and our aspirations. And as we take our next steps, we must remember that every footprint we leave is a mark on the story of who we are and who we strive to become. To understand what comes next, imagine the next lunar mission from the inside out, not from the launch pad, but from the heartbeat of the crew, from the heat of the engines, from the software making. Millions of quiet decisions each second, while no one on Earth can intervene in time. You wake in microgravity, days after leaving Earth, and the first sensation is not awe but routine. You check a display, secure a meal pouch, run a health protocol, and review the timeline for the hour. Space exploration at this stage is not fireworks. It is discipline. It is the patient conversion of risk into procedure. It is ordinary actions performed in an extraordinary place until ordinary actions become the reason you survive. Now widen the lens. Every checkbox in that timeline is the endpoint of decades of trial, failure, redesign, and stubborn persistence. The modern lunar mission carries the legacy of engineers who learned from combustion instability, from guidance drift, from thermal cracks, from valves that froze, from seals that aged in vacuum, from electronics that behaved perfectly in tests and unpredictably in flight. Space systems are not born reliable. They become reliable by paying tuition in data. A successful mission is a museum of previous mistakes transformed into hardware. This is why the moon matters so deeply to the future of deep space travel. It is close enough that help is conceivable, yet far enough that self-reliance is non-negotiable. A radio signal still takes long enough to remind you that real-time remote control is a luxury you cannot count on when seconds matter. If a warning appears during descent, there is no time for a committee back home. The machine and the crew must decide. The moon is where autonomy stops being a convenience and becomes a survival trait. Think about navigation for a moment. On Earth, we move through an invisible ocean of references. Roads, horizons, landmarks, network timing signals, magnetic cues, and dense sensor maps all support us. In deep space, those comforts fade. Navigation becomes celestial geometry with unforgiving accounting. You combine inertial measurements, star tracker observations, terrain relative cues, radar altimetry, and orbital dynamics models. You calibrate, update, cross-check, and propagate uncertainty through every burn plan. You do not eliminate error. You shape it, constrain it, and keep it away from the cliffs where small mistakes become mission-ending events. The history of this craft reaches back to mathematicians and physicists who first understood orbits as precise expressions of gravity and momentum rather than mysterious paths in the sky. Johannes Kepler described the geometry of planetary motion with laws that transformed observation into prediction. Isaac Newton unified falling apples and circling moons under one framework of gravitation. Centuries later, mission analysts used those ideas to compute free return arcs and transfer windows. In the computer age, software turned those equations into operational choreography. Today, machine vision and onboard autonomy add a new chapter, but the old math is still the skeleton beneath every modern algorithm. Fuel remains the tyrant of mission design. Every kilogram launched from Earth brings a chain of consequences that propagates through structure, propulsion, and cost. The rocket equation is often introduced as a simple formula, but in practice, it behaves like an argument with reality that you never fully win. If you want more landing margin, you need more propellant. More propellant means more tank mass. More tank mass means more lift demand. More lift demand means a larger launch stack or more launches or both. This cascade is why space architecture is fundamentally about clever staging, refueling strategies, high-efficiency engines, and ruthless prioritization of what truly has to fly. To feel this physically, imagine carrying water up a mountain where each cup you drink gives you strength, but each bottle you pack slows your climb. At some point, adding resources reduces performance rather than increasing it. Spacecraft designers live inside that paradox. They shave grams from brackets, optimize cable harness routes, redesign insulation layers, and trade hardware complexity against mass repeatedly. A few kilograms saved in one subsystem can unlock dozens of kilograms elsewhere once launch multipliers are accounted for. In no other engineering domain does 1 kilogram have such a long economic shadow. Now consider the moon itself as an engineering environment. Lunar gravity is weaker than Earth but far from negligible. That 1/6 gravity changes gate, tool reaction forces, fluid handling behavior, dust transport, and structural loads. Surface temperatures can swing from blistering sunlight to brutal cold depending on latitude and local time. Shadows near the poles can preserve ice for geologic ages, while nearby ridges receive long arcs of light that may one day power outposts continuously. The moon is not a uniform desert. It is a patchwork of microclimates and terrain regimes that demand local strategy. Lunar dust deserves special respect. These tiny grains are not like rounded beach sand softened by wind and water. Lunar regolith particles are angular, glassy, and electrostatically active, shaped by micrometeorite impacts and billions of years of exposure without atmospheric weathering. They cling to suits, seals, radiators, and joints. They scratch visors. They infiltrate bearings. During Apollo, astronauts reported that dust smelled like spent gunpowder once inside the cabin, and they experienced irritation consistent with abrasive contamination. Future missions must treat dust not as inconvenience, but as a system-level hazard. Engineers are now developing layered defenses. Suit ports can keep contaminated exteriors outside habitats. Electrostatic dust removal techniques can push particles off surfaces with traveling electric fields. Material scientists test coatings that reduce adhesion. Mechanical designers isolate critical interfaces and add sacrificial barriers where erosion risk is highest. Operational planners shape approach trajectories to reduce plume-induced dust blowback during landing and ascent. No single fix solves the dust problem. Success comes from many small protections working together, each one reducing risk just enough that the total system becomes robust. Radiation adds another layer of complexity that transforms architecture choices. In low Earth orbit, our planet still shields crews from much of deep space radiation exposure. On trans-Saharan lunar missions, that protective umbrella thins dramatically. Galactic cosmic rays carry high-energy particles capable of damaging biological tissue at the cellular level. Solar particle events can spike dose rates quickly, especially during intense eruptions from the Sun. Mission designers therefore combine shielding design, trajectory timing, storm shelter concepts, and operational forecasting to keep cumulative exposure within acceptable limits. The science behind shielding is subtle. Dense metals can block some radiation types effectively, but can also generate secondary particle cascades under certain impacts. Hydrogen-rich materials often perform better against specific high-energy particles because they slow-charge fragments with fewer harmful byproducts. Water, plastics, and specialized composites become more than structural choices. They become biological defenses. Some habitat concepts place consumables strategically around crew quarters to create additional protection, turning daily logistics into passive shielding architecture. Imagine a long-stay habitat near a polar region. Outside, the landscape is silent and stark. Inside, the crew tracks radiation forecasts the way sailors once watched barometers before storms. A solar event alert arrives. Procedures shift immediately. Experiments pause. Crew members move to a designated shelter volume where shielding mass is maximized. Communication with Earth continues, but local execution is immediate and calm because the protocol has been rehearsed many times. When the event passes, operations resume. In that cycle, you see the essence of sustainable exploration. Survival is not luck. Survival is practiced foresight. Power generation on the Moon forces another set of choices with profound mission implications. Solar arrays are mature and effective, but depend on site illumination and energy storage for eclipse periods. Batteries and fuel cells can bridge gaps, yet each storage technology carries mass, lifetime, and thermal constraints. Fission surface power concepts offer continuous output independent of sunlight, potentially enabling industrial-scale operations in shadowed regions. But nuclear systems add regulatory, safety, and deployment complexity. There is no perfect power source, only architectures optimized for specific mission goals and geographic realities. Thermal management may be less dramatic than launch videos, but it quietly determines what lives and what fails. In vacuum, heat transfer behaves differently than in atmosphere. You cannot rely on convective cooling the way terrestrial machines often do. Space systems must radiate heat deliberately through designed surfaces while surviving extreme external swings. Electronics want stable temperature ranges. Batteries degrade when pushed too hot or too cold. Propellant behavior depends on thermal state. Habitats require nuanced internal zoning for equipment, crew comfort, and life support efficiency. Thermal design is the unseen choreography behind all visible achievements. Water changes everything. On Earth, it is abundant enough in many regions that we forget its true value. On the Moon, each litre carries launch cost, storage complexity, and mission risk. That is why in-situ resource utilization is such a strategic priority. If accessible water ice can be extracted from regolith in permanently shadowed regions, then water can support life support loops, hygiene, agriculture experiments, radiation shielding, and potentially fuel production through electrolysis into hydrogen and oxygen. A reliable water economy on the Moon would reduce dependence on Earth resupply and unlock far longer mission durations. But extracting lunar water is not trivial mining. It is precision engineering in one of the most hostile operating environments humans have attempted to industrialize. Excavation systems must function in cold traps where temperatures can plunge so low that conventional lubricants fail. Volatiles can sublimate during handling if thermal control is poor. Processing plants must separate useful products from abrasive fines while operating with limited maintenance windows. Every valve, conveyor, heater, and sensor must be chosen for reliability in conditions that punish assumptions. If this sounds like building an oil refinery on a glacier in permanent night with a 30-second communication delay and no rescue team nearby, that is because the analogy is not far off. Lunar industry will not begin as a polished city of domes. It will begin as cautious experiments, modest throughput, and relentless troubleshooting. A pilot plant extracts a little oxygen. A later campaign doubles yield. A redesigned subsystem reduces downtime. Progress accumulates in increments until one day the process that once seemed fragile becomes routine infrastructure. This is how frontiers become economies. Human physiology and partial gravity remains one of the largest unknowns for long-term settlement planning. We understand many effects of microgravity from orbital missions, including muscle atrophy, bone density loss, fluid shifts, and vestibular adaptation challenges. We have far less direct data on months or years in lunar gravity. Is 1/6 gravity enough to preserve bone health with exercise and nutrition support, or will it still require aggressive countermeasures? How does cardiovascular regulation adapt after prolonged lunar stays when crews return to higher gravity environments? These questions are not academic. They shape habitat design, medical planning, crew rotation policy, and long-term settlement viability. The psychological dimension is equally critical. Isolation is not just being alone. It is living in an environment where every action has consequence. Privacy is limited, routines are strict, and the external world is physically unreachable. Communication delay means emotional support from Earth is real, but not immediate. Team dynamics become as mission critical as propulsion margins. Crew composition, conflict resolution training, cultural fluency, and leadership style all influence operational resilience. In extreme environments, social friction can consume cognitive bandwidth that should be reserved for safety and science. Picture a crew 6 weeks into a surface campaign. One member is troubleshooting a life support anomaly. Another is behind schedule on geology sampling because terrain traverses took longer than expected. A third is exhausted after repeated suit cycles in abrasive dust conditions. Nothing dramatic has gone wrong, yet pressure builds quietly. This is where mission success depends on habits that seem almost mundane on Earth. Clear communication, respectful handoffs, honest fatigue reporting, shared decision frameworks. The future of lunar presence will be secured as much by interpersonal systems as by engines and alloys. Science on the Moon will reward this effort with extraordinary returns. The lunar surface preserves a record of early solar system history in ways Earth cannot, because Earth erases evidence through weather, plate tectonics, and active geology. Ancient impact basins, volcanic plains, and regolith layers act like archives of cosmic events. By sampling different terrains with high-precision chronology tools, scientists can refine models of planetary bombardment, interior differentiation, and crust evolution. These findings feed back into our understanding of Earth itself, including the conditions that shape the emergence of stable environments where life could flourish. The far side of the Moon also offers radio-quiet conditions unique in the inner solar system. Shielded from much of Earth-generated radio interference, it is an exceptional location for low-frequency radio astronomy arrays that could probe epochs of cosmic history difficult to study from our noisy planet. Imagine listening for signals from the early universe with instruments spread across regolith plains, each antenna part of a vast scientific ear tuned to ancient whispers of structure formation. Lunar science is not only about geology underfoot, it is also about opening windows to the deepest past of the cosmos. Commercial participation introduces speed and diversity of approach, but it also requires mature governance to align incentives with long-term stewardship. Private firms can iterate hardware quickly, absorb certain development risks, and create services that governments procure instead of owning end-to-end. This can lower costs and broaden capability, yet market logic alone does not automatically protect fragile environments, preserve scientific sites, or guarantee equitable access. Rules matter. Standards matter. Transparency matters. The legal framework is evolving through treaties, bilateral agreements, and norms that are still being tested in practice. Key questions include how to define safety zones around operations, how to share scientific data responsibly, how to prevent harmful interference, and how to handle resource extraction claims without turning exploration into uncontrolled territorial competition. The Moon invites cooperation because no single nation can optimize every challenge alone. yet it also attracts rivalry because strategic advantage is real. The path we choose now will echo for generations. Economic sustainability depends on cadence. One mission every few years inspires, but it does not build an ecosystem. Regular logistics cycles do. Training pipelines do. Standardized interfaces do. Reliable launch availability does. Shared communication relays do. When you can count on transportation windows, power supply continuity, and predictable cargo delivery, planning horizons expand. Universities design longer research programs. Companies finance infrastructure with clearer risk models. International partners commit hardware contributions with confidence. Cadence converts ambition into institutions. Think of the evolution of aviation. Early flights were spectacular demonstrations. Routine flight required airfields, weather forecasting networks, maintenance standards, pilot licensing systems, manufacturing supply chains, insurance models, and public trust built over decades. Lunar operations are at the beginning of a similar transition from heroic expedition to durable system. We celebrate launches now because each one is rare. In the future, we may celebrate reliability, and that will be an even greater achievement. Education and culture will also change as lunar activity becomes tangible in everyday life. Children who watch surface operations in near real time may grow up viewing off-world engineering as a normal career path. Art, literature, and music will absorb the emotional texture of living between worlds. Philosophical debates about identity, belonging, and stewardship will deepen as human communities form routines beyond Earth. Exploration reshapes not only maps but also meaning. There is also a moral question that cannot be ignored. If humanity gains the capacity to inhabit multiple worlds, what obligations do we carry with us? Do we repeat patterns of extraction without foresight, or do we design institutions that reward restraint and regeneration from the beginning? Do we treat new environments as disposable frontiers or as shared inheritances requiring humility? The moon gives us a rare chance to build governance and culture before large-scale settlements hardens bad habits into tradition. From a strategic perspective, the moon can function as a training ground for Mars while still being valuable in its own right. The operational lessons are immediate. Closed-loop life support maintenance, surface mobility under communication delay, habitat reliability under abrasive dust and thermal extremes, distributed autonomy for robots and crews, resource extraction under tight energy budgets. If these systems can mature on the moon where rescue and resupply are hard but plausible, they become stronger candidates for much longer Mars campaigns where failure recovery options are severely limited. Yet the moon is not merely a rehearsal stage. It is a destination with its own science, its own economic potential, and its own cultural significance. Treating it only as a stepping stone risks underestimating what can be learned and built there. A mature lunar program can support astronomy, planetary science, materials research, biomedical studies, and industrial demonstrations that benefit life on Earth. The technologies developed for extreme efficiency in water recycling, energy management, telemedicine, and autonomous operations can return dividends across terrestrial sectors. Imagine future disaster response systems on Earth borrowing reliability principles from lunar habitats where failure was never an option. Imagine remote medicine networks in underserved regions using protocols refined for crews months from home. Imagine modular clean energy systems inspired by lunar microgrids operating in places where infrastructure is fragile. Space exploration often appears distant from daily life until you trace the engineering lineage of tools that quietly become essential at home. As flight rates rise, mission architecture may diversify. Some campaigns prioritize science at polar sites. Others focus on infrastructure deployment such as communication towers, navigation beacons, and power nodes. Cargo-first strategies can pre-position habitats and consumables before crew arrival, reducing immediate risk. Robotic precursor missions can scout terrain with high-fidelity maps and geotechnical data informing landing zone selection and construction planning. Over time, surface operations could evolve from isolated missions to networked outposts with shared services. Construction on the moon will likely begin with pragmatic methods rather than monumental visions. Berms of regolith can provide radiation and micrometeorite shielding. Inflatable modules may offer high volume to mass efficiency for early habitats. Sintered regolith bricks or additive manufacturing approaches could create pads and barriers that reduce dust during repeated landings. Each method carries trade-offs in energy consumption, equipment complexity, and repairability. The winning approaches may differ by site and mission phase rather than one universal design. Transportation between lunar orbit and surface will also evolve. Early systems may rely on specialized landers with narrow mission envelopes. Later generations could emphasize refuelability, maintainability, and common docking standards across providers. Surface mobility may progress from unpressurized rovers to pressurized traversers capable of multi-day expeditions. Communication networks may shift from direct to Earth links toward resilient mesh relays in orbits and on-terrain high points. In frontier engineering, flexibility is often more valuable than elegance. Throughout all of this, the language of risk must remain honest. Every mission carries non-zero danger. Complex systems fail in complex ways. Unknown unknowns do not disappear because schedules are ambitious, or headlines are ambitious, or headlines are exciting. What responsible exploration does is make risk visible, measurable, and governable. It builds margins where they matter most. It rehearses contingencies until teams can execute under stress. It encourages dissenting technical opinions before irreversible decisions. It rewards those who surface weak signals early, rather than those who hide uncertainty behind confidence. This ethic has deep roots in the history of exploration and engineering. Many hard lessons in aerospace were written in investigations that transformed tragedy into safer design practices. Fault trees became more rigorous. Redundancy philosophies matured. Human factors engineering gained prominence. Simulation environments grew richer. Independent review structures strengthened. The culture of modern mission assurance is built on remembrance as much as innovation. To honor past explorers is to refuse complacency. At the same time, caution cannot become paralysis. Progress requires decisions under uncertainty because perfect information never arrives on schedule. Leadership in this domain is the art of balancing urgency and prudence without surrendering to either extreme. Move too fast and hidden fragilities dominate outcomes. Move too slowly and capability atrophies, talent disperse, and strategic windows close. Sustainable momentum comes from iterative milestones that are ambitious enough to matter and disciplined enough to survive reality. If we succeed, future generations may inherit a world where Earth and Moon are linked by routine transport, shared industry, and continuous science. They may look back at our era as the hinge point when spaceflight transitioned from episodic heroism to enduring civilization-level infrastructure. They may see Artemis-era missions not as isolated events, but as the foundation stones of a much larger architecture of human presence beyond Earth. And yet the deepest reason to go may remain profoundly human rather than purely technical. We explore because understanding enlarges us. We build because possibility compels us. We look up because wonder is part of our species' identity. Standing on the Moon and seeing Earth rise above a horizon of ancient dust compresses politics, borders, and daily noise into a single luminous thought. Home is one world. Life is precious. Responsibility is shared. When a crew member kneels to collect a sample, that motion carries more than scientific intent. It carries continuity with every thinker who ever asked what the sky is made of. It carries the curiosity of children who have not yet learned to call impossible things impossible. It carries the discipline of teams who spent years solving unglamorous details so that one careful action on another world could happen safely. In that moment, abstraction becomes touch. The Moon will test our machinery, our institutions, and our character. It will reward patience over spectacle and cooperation over vanity. It will force us to integrate science, engineering, economics, ethics, and imagination into one coherent practice. The challenge is vast, but so is the opportunity. Not simply to visit another world, but to become the kind of civilization that can do so wisely, repeatedly, and with a sense of shared purpose. So as the next missions rise on pillars, fire, and arc into the dark, remember that the real journey is larger than any single launch. It is the slow construction of trust in systems, in teams, in data, in values, and in each other. It is the conversion of distant aspiration into everyday capability. It is the story of a species learning, step by step, how to live in a wider universe without forgetting the fragile world that taught us to dream. One day, perhaps sooner than we expect, the child will ask what it's like to go to the moon in the same tone used to ask about crossing an ocean. The answer may include pressure suits and docking maneuvers and regolith chemistry, but underneath it all will be something older and simpler. We went because we could learn. We stayed because we could build. We returned because Earth is home. And we kept going because the horizon, once reached, always reveals another horizon beyond.